Swayam Prabha. Digital India. Educated India.
Hello, welcome to the last week of the course. Here we will be talking about a new topic, that is buckling. So, all this time we have been discussing how to analyze a beam or a component of an aircraft, thin walled, under different torsional, bending and shear load. And we were mostly studying the stresses developed at different points on the cross section or the distribution of the stresses, and to find out the maximum value of the stresses that is occurring in a cross section. So, the point was that the most important objective was to see whether the maximum value of the stress developed is less than the ultimate stress or ultimate strength of the material, so that the material will not fail under when deployed. In this week, we will move into an entirely different topic, which is called the structural instability, or there are various forms of structural instability. We will be dealing with the buckling of a column as a part of the structural instability. Now, I am sure all of you are acquainted with buckling, acquainted with column buckling. So, what happens is that if we have a slender column, and if we apply an axial compressive load, let us call it P, and let us increase P gradually, then at a certain value of the P, that is called the critical load, the column starts to bow or buckle and thereby undergo large deformation, which will lead to large stress and strain and eventually the failure of the structure. So, in other words, we can say that if an increasing, let me put this in words, if an increasing So, this is what can be expressed in a very laymanish way what is meant by buckling. So, let us see the important points. So, if an increasing axial compressive load is applied to a slender column. So, these are the important points. There is a certain value of the load which is called the critical load, critical buckling load. Then the column will bow or buckle in an unpredetermined direction. So, this buckling will be of large deformation which will eventually give rise to large stress and strain, and that will lead to failure. Okay. So, now this critical buckling load that we are talking about is much smaller than the compressive failure load of a column. So, this critical buckling load is most often much smaller than the compressive failure load. So, like the ultimate strength in tension of a material, there is also an ultimate strength of in compression for the material. So, if I apply an axial compressive load, it will also fail in compressive failure, that the applied compressive stress will exceed the ultimate compressive strength of the material, and the material can fail. That is of course a mode of failure of a column. But now, if we have a slender column, the column is going to fail at a load which is much lower than the load corresponding to the compressive failure load, and that load is due to the buckling failure of the column, and that is called the critical buckling load. So, buckling is predominantly effective or is a concern for slender column. For very stout column, the compressive failure load is smaller than the buckling load. So, before it fails in buckling, it will fail in the compressive failure, in compressive failure. But in slender column, where the thickness by length ratio is very small, the buckling load is going to be much lower than the compressive failure load, and the column will break or will fail under buckling. Now, in aerospace structures, as we have seen in the last several weeks, that we usually all the reinforcement, that are stringers, spars and longerons, are thin-walled long beam. So, they falls under the category of slender beam. Additionally, the skin are also thin-walled, so they are also very vulnerable to buckling. Therefore, the monocoque structure of an aircraft, the stringers, spars and longerons of an aircraft are very much vulnerable to buckling failure. Therefore, it is important in aerospace structure to understand buckling very clearly. Now, all this that we have talked about, this entire thing that we have talked about is going to happen when the column has a geometrical and or material imperfection. Or the applied load and or, of course, now this entire buckling phenomena is going to happen when the column has a geometrical or material imperfection. That is, there are some inhomogeneity in the material is not evenly distributed, the support conditions are not perfect, there is some misalignment in the support condition, there are some asymmetry due to the manufacturing process. So, all this imperfection either in geometry or in material will lead to this kind of buckling phenomena. Even when the load is applied is not completely aligned with the centroidal axis, it has some form of eccentricity, it is slightly off than the centroidal axis, or there is some misalignment between the two loads, then also the column becomes vulnerable to buckling failure. Now, in reality, however we try to make a perfect column or to apply the load perfectly through the centroidal axis, it is practically infeasible, because there would be even the slightest form of imperfection either in the geometry or in the material or in the application of the load. Therefore, in reality, almost all the columns that we encounter, or almost all the slender columns that we encounter will be susceptible to buckling failure, will be vulnerable to buckling failure. Therefore, it is very important for us to understand buckling carefully. Now, the theory of buckling was proposed by Euler in 1744. So, the theory is called the theory of column buckling. Or Euler theory of buckling, Euler buckling of column, similar to and this was proposed by Euler in 1744. So, the buckling theory that is used even today is based on this Euler buckling of column, or the theory Euler's theory for buckling of column. Now, let us try to understand what is Euler theory of buckling and what is meant by the critical buckling load, and how are we going to find out the critical buckling load. Now, let us consider a perfect column. Let us say that we have a perfect column Now, if we take a perfect column, then let us write it down. Now, if we have such a hypothetical situation or theoretical situation where we have a perfect column, there is no form of inhomogeneity or heterogeneity in the column or any asymmetry in the manufacturing of the column, and the load P, the axial compressive load, is applied perfectly through the centroidal axis. In this hypothetical or theoretical case, buckling will not happen. Whatever or however, whatever the large value of P, so this should be understood first, that if we have a perfect column under perfectly applied axial compressive load P, then whatever be the value of the P, the column is not going to buckle. Now, therefore, what we do is that we apply a small lateral load F, and because of this lateral load, the column will deform laterally, and since the load is small, let us assume this deformation V Z, Z being the lengthwise axis. So, this is Z. So, V Z is small lateral deflection. So, let me write it down. V Z is okay. So, the axial loads are still there. Apart from that, I apply a sideway force F, so that it deforms laterally, and let us call that the lateral deflection is V Z, which is very small. Now what happens? Now there will be three possibilities. Now, if the applied axial compressive load is less than a given then a certain critical load, where P critical is the critical buckling load. We do not know what the critical load is, but let us assume that we know what is the critical buckling load. So, if P critical is the critical buckling load, then under the case when the applied load P is less than P critical, then the deformation the lateral deformation or the column will return to the undeformed state when the load F is removed. Now, as long as the axial load P is less than the P critical, then the column is going to return to the undeformed state once the lateral force F is removed. So, this is called the stable equilibrium. Now, the second case is that when P is equal to P critical, when the compressive load is equal to the critical value P critical, then what happens? Then the column will remain in the deformed shape when F is removed, but will not deform further. And this gives us the neutral equilibrium condition. And finally comes the third case where P is greater than P critical. Now, when P is greater than P critical, the deformation of the column keep increasing, and it is in unstable, keep increasing, and this therefore is under unstable equilibrium. Right. So, this condition is a cause of concern, because the deformation can just keep on increasing and can go to a very large deformation, thereby producing large strain and eventually large stress and failure of the column. So, this is what is of concern, and therefore, it is important to find out what is the P critical for a given column. Now, let us attempt to find out what is the critical load P critical for a pin column. Or let us just do it in a fresh page. So, let us try to find out critical buckling load P critical for a pin column. Now, so let me first draw a now the ends are pinned. Let me draw the axis. So, this is the Z axis or the lengthwise axis, this is the Y axis, and this is the X axis. Now, this is the length of the column L, and an axial compressive load P is applied at the two ends of the column. Now, because of this applied force, let this column undergo a deformation, and let this deformation be referred as Vz. So, now let us try to find out the equation, the governing equation for this portion. So, let us take a small portion of the column and let us draw the free body diagram. Now, the forces on this is going to be P. Now, because of P, there would be another internal force P, and to have a moment balance, there would be an internal moment M. Now, if we write down the moment balance equation, what do we get? We get M plus PV is equal to 0. Now, again we know that M is equal to EI d2V by dz square. So, now plugging this in here, we can write EI d2V by dz square plus PV is equal to 0. So, let me call it as equation 1, and this equation is the governing equation of the column, pin column under axial compressive load P, undergoing a possible deformation of P. In the next lecture, we will be trying to solve this equation. Thank you.